I've gotten into this habit of playing a little bit of piano in the morning, and sometimes it's just for 5 minutes, and it doesn't even matter what it is that I'm doing. I just kind of sit down there, and I realize that by the time I get on my bike to go to work, I'm just feeling so much better than when I woke up. And you know, I wake up often, I'm feeling kind of hopeless, and I play this music, just this little bit, and the other day I was on my bike and I was thinking, oh, that's music therapy. and yeah, it seems to work. So, I get to talk to you about music for brain health, and let's start. Grass is rustling, and the guy who made this sound for me is Gary Rydstrom, who created the sounds for Jurassic Park. Right, so, anyway, this animal needs to be able to figure out whether he should stay or he should go. And making sense of sound is one of the most complex jobs that we ask of our brains, and it's complex because what happens is that sound has to enter our brains, and from there it is informed by how we think about sound, how we perceive it, how we move with it, and how we feel about it. So we call this cognitive, sensory, motor, and reward system. And I need you to listen to this. Tell me if you can hear a sentence. Here's the sentence you should have heard.
The juice of lemons makes fine punch.
Now, here is the sentence I played for you the first time. You believe me? So what we know about sound very much influences how we hear it. Wow. So we live in a materialistic world, and you know, if you can't see the thing, you don't pay attention to it. And we know that a visual object has all kinds of ingredients, like how the color, the shape, the size, how it feels. It turns out that with sound, sound, as you know, I don't have to tell this group, that sound has just as many ingredients: pitch, timing, timbre. There are so many ingredients and nuances of sound qualities, but we don't think about it so much because sound is invisible. And so many of the world's most powerful forces, like gravity, neutrinos, so many elements of our world are in fact invisible. So we need to realize how incredibly powerful sound is, because it is hugely, hugely powerful. So one of the things that we now can do with neuroscience is that we can measure the brain's response to sound. Right now, as I'm talking to you, the nerves in your brain that respond to sound are producing electricity. Electricity is the currency of the nervous system, and with scalp electrodes, we can pick up that activity. I want to tell you just a little bit about my personal history and how I came to this. My mom was a pianist, and when I was a little girl, I would play underneath the piano because that was where it was just felt good to be. And I also lived in a house where a number of languages were spoken. So sound really carried a lot of meaning. And when I became a neuroscientist, I was studying the effects of learning in animal models, and really being able to look at individual neurons and seeing how neurons changed with our experience. But I wanted to be able to have this kind of precision and objectivity that we have with basic biology for humans. And we can now do this. So if I measure your brain's response to sound, I use a mixing board here because I am picking up all the different ingredients of sound that your brain is processing. It's not a volume knob effect. the pitch, the timing, the timbre, these are all changing in different ways based on your life in sound. So if you have certain expertise, the mixing board will change in a way. If there are certain disorders, it will change in another way. But what is important is the tremendous granularity and precision that we have. Because you see a sound wave going into this little boy's ear, into his brain, and then you can see the brain wave that his brain is eliciting. And what you can see right away is that the sound wave and the brain wave physically resemble each other, and they resemble each other so much that we can actually take the brain wave and play it. Wow. So here's the sound wave, it's a speech sound.
Da.
And here's the brain's response to sound.
Da.
Wow. Here are a number of other examples.
Da. Da.
You'll hear a scale and the brain's response to the scale. Little Mozart, and then the brain will come in. And the muscular sounds. Okay? So the fact is, we have a lot to work with. And later, at the end of my talk, I actually have a keyboard here with, these are brain responses that have been sonified. We have been able to record the responses of each one of these notes for individual people. But imagine having all of this information to work with. So now as scientists, the big question is what is going on in our brains when we make music? And what is the impact of what you do on the nervous system? We want to be able to understand that better because we really don't understand too much yet. So this frequency following response, that's what this response is called, that we're able to measure with such great precision in humans with just a couple of scalp electrodes and an earbud or two. The measure is objective, it's very well vetted, it's mobile, it's fast, it's repeatable, and it's uniform. You can get the same response in a baby and in an older person. So I invite you, and I will invite you multiple times, to visit our website, BrainVolts. And you will find a lot of information there. It's really put together for you. It's a labor of love. But on the home page, there's a demonstration of our biological approach. And so you can really understand a little bit about how it is that we record these responses. It's a little video that takes 2 or 3 minutes to listen to. Okay, so I talked about making sense of sound and how it makes us engage our cognitive, sensory, motor, and reward pathways. Well, music is the jackpot, right? So we know that making music, and we have a lot of science to back this up from not only our own lab, but globally, we know that making music, and it is making music. I'm going to get this question out of the way right away. People say, oh, I listen to music all the time.
Yeah.
Is that going to change my brain in this fundamental way? And I tell them, you are not going to become physically fit watching sports. So let's disentangle a little bit of the sensory, cognitive, and motor reward systems, and a little bit of what the neuroscience has revealed. So in terms of cognitive function, I'm going to play a tone, and as soon as the tone comes on, I want you to raise your hand and then immediately put it down, and do not move when you hear the siren. So just figuring out, this is about as basic as it gets, right? And just figuring out what to pay attention to and what to ignore is very difficult. and is something that we need to teach our brain to do all the time. And what we know is that people who are musicians, and when I talk about musicians today, I am talking about people who actively play a musical instrument. I'm not talking about professional musicians necessarily. I'm talking about people who will play music regularly, say for a minimum of 20 minutes twice a week. So on a regular basis. And so we know that people, musicians, defined this way, are better at knowing what to pay attention to and what to ignore. Auditory working memory is important. If you did not remember what I've just said, you will not make sense of what I'm saying right now. And there are many tests of auditory working memory, like I can ask you to repeat back the names of animals that I've just given you, and you need to think about, okay, so which animals start with the letter B? So it's not a matter of just repeating back what I said. You have to think about, okay, which ones start with B? And that's using your auditory working memory. And as a musician, you are exercising your auditory working memory all the time, and so it helps you for all kinds of things. And we know that, again, musicians are simply better than non-musicians with auditory working memory across the lifespan. And I do want to play for you this personal, kind of embarrassing example of me exercising my auditory working memory while I'm learning. I'm trying to learn this Chuck Berry lick. So he's going to play, and then it's really obvious when he's playing. And then you'll hear me attempt to remember and to engage the physical complexities that it takes to play. And then, of course, I'll forget, and I'll need to listen to him again, and it'll just kind of go back and forth, but it's an illustration of auditory working memory. Many times, and a lot of exercise of auditory working memory. This is work that Charles Lim has done, where arguably one of the most creative things that we can do as human beings is to improvise. And so he was interested in, well, what is it that might happen in the brain while we improvise? And so he was able to get a number of musicians to improvise on a keyboard while they were in an MRI scanner. And what he found was that the areas of the brain that we know ordinarily inhibit what we do were actually less active, and the areas of the brain that we know are important for creative action were more engaged. But I think what is very important is it's never just a matter of more. It's a matter of looking at these intricacies in different circuits and seeing that what is very important is the ability to inhibit a lot of the information that you're getting from so many of your systems and your years of your experience in order to shut some of that down and to channel it into the creative improvisation that you're doing. So sensory motor, the way, we've seen this so many times, the way we move together is very important, and it engages us in a way that, in terms of mutual understanding and conflict resolution, we become much more likely to interact positively with each other if we move in sync together. So this is work from Laurel Trainer's lab. And she has babies that are bouncing in sync together with an experimenter.
There.
Now, hold the baby, help the experimenter.
Oopsie.
She needs help.
Uh-oh. No.
bouncing out of sync.
There. Uh-oh. Oh no.
So, if we could just get our heads of state. Okay, so how about our reward system? We've talked about cognitive, sensory, motor. Let's talk about reward. I want you to look at these babies. When the music starts playing, look at how they interact with each other.
Hi girls! It's August 6th. Is that right?
Yeah.
August 6th, 2012. Daddy's gonna play them a little song while they're eating their peas.
You guys ready?
I love playing this video because now I look at you and everyone has sweetened up. And, I mean, look at your neighbor. Everybody's smiling. So what is happening in our brains to create this kind of emotion? And this is work from Robert Satori's lab, where he had people choose music that they loved, and he measured dopamine levels. And what he was able to determine was that the areas of our brain, our limbic system, which is our reward system in the brain, and it produces dopamine. Dopamine was produced both in anticipation of the exciting part of the musical piece that they knew, and another part of also the limbic system, so this is the same emotional system in the brain, released dopamine at the point of the musical climax. So we know, I mean, you know, we are a bag of chemicals, as my 9-year-old very eloquently said. It's beautiful to be able to see objectively what it is that is going on, at least one little piece of what is going on in our brains when we are listening to music that we know elicits an emotional response. So, aren't these boys beautiful? They're beautiful, right? So, these are my babies. And you know how good it feels to hear the sound of someone's voice that you love. Why is that? You know, and you pick up the phone and you say, oh, it's so good to hear your voice. And it's because of the years of pairing sound to meaning, sound, cognitive sensory reward processing in the brain. And you need to know, we are what we do, and our life in sound sculpts how we will automatically respond to sound. So our default system has changed based on our life in sound. And one of the most exciting experiments that just got me thinking this way was some work that Ravi Krishnan did at Purdue, where he took speakers of tonal languages and measured these kinds of responses that I talked to you about today, these FFRs. And he measured them in people who spoke tonal languages in response to these dips that happen in pitch within a syllable that don't happen in a non-tonal language. And what he found was that in their sleep, speakers of tonal languages followed those contours, whereas speakers of a non-tonal language speakers just simply did not. And it becomes so automatic. So it's very important the choices we make, how we spend our time, because we are an evolutionary experiment. And within the course of our lives, we will change based on what we do, and certainly our hearing changes. How we perceive the world will change based on our life in sound. And again, biologically, I love to be able to, I work with signals, sound waves, brain waves, and we wondered whether people with musical experience, when they listen to an emotional sound, like a baby crying, would they respond differently? And so the musicians are in red, the non-musicians are in black, but what is very interesting is that this part of the waveform is the complicated part of the waveform, and that is the portion that the musicians responded to with much, much more precision, and this is, again, automatically, compared to the non-musicians who actually are responding more vigorously to the simple portion of the sound, because that's what they have. That's what they have to work with. So it's very important to, again, just be thinking about the impact of our musical experience, our language experience, on how we process all kinds of other sounds. So how can music help us for everyday communication? And I'm very interested in the communication skills, and these are very early development skills. They are skills that we need throughout our whole lives, which is language and hearing and noise. And what we find is that language, listening, and music coincide in ways that we can measure biologically. So if we think about rhythm, so rhythm, you all know that rhythm is obvious in music. But you don't think about, this is one of the reasons I need to move when I talk, that rhythm is very involved in how we speak. And this illustrates the effect, I think, very well.
Mr. Walker, I am extraordinarily busy, sir. I just wanted to ask about the chocolate. The lifetime supply of chocolate for Charlie. Well, when does he get it?
He doesn't.
Why not?
Because he broke the rules.
What rule? We didn't see any rules, did we, Charlie?
Wrong, sir. Wrong. Under Section 37B of the contract signed by him, it states quite clearly that all offers shall become null and void if, and you can read it for yourself in this photostatic copy, I, the undersigned, shall forfeit all rights, privileges, and licenses herein and herein contained, etc., etc. Fax mentis incendium gloria culpum, etc., etc. Memo bis punitor delicatum. It's all there, black and white, clear as crystal. You stole fizzy lifting drinks. You bumped into the ceiling, which now has to be washed and sterilized, so you get nothing. You lose. Good day, sir.
You're a crook. You're a cheat and a swindler. That's what you are. How can you do a thing like this? Build up a little boy's hopes and then smash all his dreams to pieces. You're an inhuman monster.
I said good day.
So rhythm is important for speech. And we know there is a lot of biological research that has told us that even just tapping along to a beat is something that tracks with with language skills. And so here are these two little guys tapping along with an experimenter. This guy synchronizes to the beat. Pretty good. And this guy. He's only 3. And he's enthusiastic. What is very interesting is that, there are these rhythms in sound, and what we can see is that the synchronizers, again, automatically, they follow those changes in amplitude modulation of the sound. Their brains follow that better than the non-synchronizers, and importantly, they have better, more developed language skills. We also know that drummers, in particular, are very good at well, musical experience will help us all hear speech and noise better. But there are certain aspects of hearing a noise that are especially brought out in drummers, and I want to explain that in just a minute. Because the fact is, there are different rhythm intelligences. So as a scientist, I am so often wrong, which, you know, it's great, because otherwise, if I knew the answers, why would I do the experiments? And one of the ways I was wrong was I thought that if you were good at rhythm, you would be good at all different kinds of rhythm tasks. And so we have different rhythm tasks in the lab. And what we found is, one aspect of rhythm is the pulse, right? Another aspect of rhythm is what we might call the rhythm sequence or the rhythm pattern. You know, so if you're going da 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 or da 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 da, okay? And I thought if you would be good at one, you'd be good at the other. It turns out that there is no relationship at all. And think about the fact, I mean, this is very important, that in music, like just in a measure, you know, as you're reading a musical score or as you're improvising, you have both the pulse that you're keeping track of, and you have these patterns that you're playing upon it, and yet these skills they engage different areas in our brain and different kinds of neural processes. So that we have these different intelligences, and interestingly, following the pulse seems to align more with language skills, and this rhythm pattern perception and also production is something that aligns more with hearing a noise, which is something that the drummers are especially good at. And importantly, in terms of looking at the brain's response to sound, and we look at different synchronous events, there are different aspects, different brain processes that are involved in these two different kinds of rhythm listening. So now, I'm going to have you tap along, and what you need to do, this half of the room is going to be following the pulse, and we're going to be listening to You Are My Sunshine. You're going to see an adorable person playing the guitar. You will play along with them. This part of the room will be following the rhythm sequence, so, you know, essentially the words. And here we go. So, you guys are pros. This is the second time I've tried this with an audience. I did have an audience at the Fermi Lab a couple weeks ago, and we did this, and they did not have it. You guys are, I mean, there wasn't a single person who wasn't doing exactly what, again, you're pros. So, you know, how might we train these rhythmic skills? And you know, there are different ways of doing it, as you very well know. And one way is digital medicine, digital music medicine. There's this program, Interactive Metronome, that some of you may be familiar with. Interestingly, we've investigated some of the underlying brain processes that happen with interactive metronome. And we found that these different skills that I talked about, these different rhythm intelligences, they both seem to be captured by this very slow rhythmic tasks that involve the integration of your different modalities. And again, one's ability to perform tracks with language skills. So we found that interesting. In terms of neuroeducation, so, you know, I've been saying, okay, well, we have some biological evidence that is telling us that making music might be good for our nervous systems. Well, what about what we actually do? So what about music therapy? What about music in schools? So what we have done is we have brought our labs into the classrooms. And what we have wanted to do is to look at the impact of music education, and we happen to do this in low-income neighborhoods in both Chicago high schools and in the gang reduction zones of LA. And one of the things that we know tracks with poverty is linguistic deprivation. And it's known as the 30 million word gap. And kids whose moms have less education are likely to hear 30 million words by the time they're 3, compared to a child whose mom is more educated. So what we did is we took these kids educated in the same schools, the kids were educated in the same schools, in the same neighborhoods, and we simply divided them based on their mom's education. And we found that the kids whose moms had less education had more neural noise, so asynchronous noise, in their biological responses, and importantly, their biological response to sound was not as precise. And so I think of this analogy. Imagine that you're listening to the radio, and there's static in the background, and on top of it, how is a child to learn? And so one of the things we wanted to know, so we have this signature for linguistic deprivation, a neural signature that certain aspects of harmonics, how stable the response is diminished, and the noise in the response is very high. What we found is that music making over a number of years doesn't fix the problem, but it partially offsets it. And we can see this in very rigorous biological, objective terms. There's nothing a child can do to sandbag or to rig the response. You know, if I measure your response to sound, it is what it is. But you know, you always may want to know, does music improve sound processing in the brain, or are people drawn to play music if they are born with certain skills? And really a way of looking at this is to do a longitudinal study. And believe me, the long and longitudinal study is no joke. We have done these longitudinal studies over 4 years in Chicago public schools and in Los Angeles. And again, as you know very well, it takes time for people to learn. It takes time to change the brain. But what's important is to have groups that are matched at pretest. So they're matched on language skills, on listening, and on sound processing in the brain. And then you give one group music and another group an active control, and you randomly assign them to different groups. And you know, what we were able to find is that, and I'm sparing you the data here just for time, but if you go to our magical website, especially under advocacy and under neuroeducation, you will find, and these papers, we've written up our findings in some of the world's best journals, so they're there for you to read carefully. But we found, essentially, that language skills improved in the music groups. Listening skills, so listening, I really am talking about listening to speech and noise. And sound processing in the brain, the kinds of brain responses to the different ingredients of sound on the mixing board that are so important, not only for music, but for language and for hearing other sounds. These were enhanced in the music groups. But what was important is that in both of our studies, we saw no evidence of biological changes after 2 years of music making. I'm sorry, after 1 year of music making, we saw nothing. It was only after 2 years that we started seeing these fundamental biological differences and changes in the brains of the kids who had actively engaged in making music. So, again, in everything that we do, it's not what we do for 5 minutes, it's what we do for a long time. And you spoke this morning about the choices we make, right? And so it really is very much about the choices that we make and how we choose to spend our time for a while. But, music education is not something that you can just turn on with a pill. And it is not something that is good to throw some money at for 5 minutes. Importantly, it has a lifelong impact. So, how many of you have played an instrument sometime in their lives? How many of you are still actively playing an instrument? Yeah, oh yeah. So that's most of you, but in many audiences, a lot of people have played music at one time in their lives for a number of years. But they're not continuing to play. But the fact is it has a lifelong impact. And the music that you made early in your life, and again, we have biological data that shows that, for example, as we get older, the neural timing in our brain slows down. But if you have been someone who has made music and made those sound to meaning connections early on for many years, you carry that through your life when you're 70, 80, 90 years old. And so one of the things, again, just to show you the biology, this is a typical response from a young adult and the typical older adult. And here is an older adult musician, which you see is a biologically younger brain. And the question that others will ask, is it ever too late to start? No. We know that, again, biologically, I'm a biologist, and in very controlled animal models, we can see that the nervous system will constantly change, and we learn, we change, we adapt until we die. So let's think about healthy brains especially exemplified by musicians, and hurting brains. An area that we have been looking at a lot in my lab these days is concussion. And so you think, okay, so what does this have to do with sound? Well, a lot of you, probably all of you already know, sound processing in the brain is one of the most complex jobs that we ask our brains to do. Yes, because it involves our sensory, cognitive, motor, and reward systems, but also because so sound, there is information in sound waves that happen on the order of microseconds, which means that your brain has to make computations on the order of microseconds. This is actually faster than neurons fire. So our hearing system, much more than our visual system, which is more static, operates at very, very, very fast time scales, because sound, by definition, it is fleeting, it moves, it doesn't stand still. And so, of course, if you get hit in the head, this very, very delicate, precise machinery is likely to be disrupted. At least that's what we thought, and these are areas where others and we are proving to really be right. We know that people who have had sustained blast injuries, war veterans, have had difficulty. There's a good literature showing that there is difficulty hearing speech and noise. So, for example, if you listen to the sentence, tell me if you can hear a sentence. It's kind of hard to pull a sentence out. This is a little easier.
Sugar is very sweet.
Okay, so these are the kinds of tests that veterans really have a lot of trouble with. We also know that athletes have trouble with this. And we've recently published a study where we took athletes from the same clinic. Some kids had musculoskeletal injuries and others had concussions. And you could see that their hearing and noise abilities of the concussed kids was worse. It was not only worse at the beginning, but during the 5-minute course of the session, it got progressively worse from fatigue. whereas the other kids with the musculoskeletal injuries, if anything, they got better over time as they learned the task. So we know that there is a connection between concussion and hearing and noise. We also know that there is a connection between sound processing in the brain, this FFR, this frequency following response that I've been telling you about, and hearing and noise. So there is a good, solid connection there, and so our question was, well, what about, can we biologically measure responses to sound in people, concussed athletes? And what we're interested in is we're looking for objectivity in the assessment, diagnosis of concussion to help us figure out when can we return to play, return to learn, and importantly, and especially importantly for this group, is treatment outcomes. So our first paper that we published in Nature was a paper that showed that it was a small sample, but it did show that the FFR, we had a biological marker that identified concussion 90% of the time. And so this has given us a lot of excitement and reason to press onward. So I want to focus just on pitch, timing, and timbre, and just give you a thumbnail sketch of what we know right now. Because if we look at an athlete who has just had an acute injury versus one who is recovering and one who has recovered some time ago in terms of their symptoms, but we're looking at long-term effects, what might we see? And basically what we see is that after an acute injury, so we've been following Northwestern's football team for the last 2 years, and we follow them at the beginning of the season, at the end of the season, and if they have a concussion, we measure their brain's response to sound within 24 hours of the event. And we find that pervasively, for pitch and timing and timbre, we see disruption in sound processing in the brain. In another population where we have followed kids for 2 or 3 months as they become progressively asymptomatic, these are kids who have concussions that don't resolve right away, they don't resolve within a week or two, but they resolve, the symptoms resolve after a few months. And we see that pitch and timing are continue to be problems, and that this tracks with symptom severity. And finally, long term, what is the legacy of a concussion? And one of the things that we did is we measured our football players. So these are all healthy guys who we just simply divided them, all 105 of them, on the basis of a history of a previous concussion. And we found 30 of them, 25 to 30, who had had a history of a previous concussion, and we position matched them with other members of their team, and we found that there remained a legacy of one particular aspect of sound processing in the brain that was diminished compared to their peers. So we clearly need to learn a lot more. We're following youth football, adolescent, college, professional athletes, and we're looking at a variety of sports in boys and girls, and we just landed an NIH grant to study in our athletics facility, and I have wonderful, wonderful colleagues at Northwestern, trainers and physicians, and we are going to be assessing all 500 athletes in all of our sports longitudinally over 5 years, beginning at the end of the season and then as they receive and recover from concussion. So let me talk about treatment for a minute, because so for treatment, it has been symptom targeted for concussion, so vestibular, physical therapy, exercise, academic accommodations, and psychological care. But where does music fit in, right? So there is a history, especially in the military, of music making and the ability of music making for recovery of head injury. So if we think about concussion, I want you to pay attention to this idea of hearing a noise and rhythm that you've heard about. Here is Renee Fleming, who is singing with Colonel Avila this was on Memorial Day on Capitol Hill. And this is his music therapist, and they're singing "God Bless America." It's really beautiful, but the way and he talks about how music therapy helped him regain his voice and his connection to the world. So we do know that across the lifespan, one of the problems that we have with a head injury is difficulty hearing a noise, but we also know that people with musical experience are better at hearing a noise. And we know this, again, across the lifespan, and beautifully, we can see this in the brain's response to sound. So here is the brain's response in quiet in a musician, and you can see that the response in noise is almost as good. It really has not been disrupted by the background noise, whereas the non-musician has a pretty solid response in quiet, but he really takes a hit in noise. So remember, we talked about drummers and music and various aspects of rhythm as being important for communication and language skills, and especially hearing a noise. And I'm mentioning again this interactive metronome, which seems to track with both kinds of rhythm skills, and it's something to just be thinking about as you think about therapy. Is, you have therapy that engages each one of you, and there is no substitute for a personal therapeutic interaction. On the other hand, there's help that can be obtained through what we can think of as digital music medicine. And so, again, this is an area that I hope will become more and more evidence-based in terms of the data that we can have to draw on, so that it can help you make various choices about how you may want to integrate and supplement some of the work that you do. So I'm going to leave you with this notion, again, that the NIH has been very interested recently in funding music-themed work. And I was involved about 1.5 years ago with a workshop that had not only neuroscientists, of course I knew I'd better know that work, but I didn't know many of the music therapists, and I have just been learning so much about music therapy. And Francis Collins, who's the director of NIH, asked his 23 institutes of the NIH whether they could see music as being a part of their individual portfolio. There's a neurology institute, an eye institute, infectious disease institute, and 21 of the 23 institutes said yes. Wow. And so there was an event last year, there's going to be another event at the Kennedy Center again this fall, but where they looked at both the neuroscience and the therapeutic aspects in children, in adults, and in the aging brain. And this is me with Renee Fleming singing her song to the moon, Rushalka, which she just did so beautifully. And while she sang, I kind of sat there and then needed to speak about what is it in music that engages our emotional system biologically. And it was really, it was a moment for me, because I felt so biologically engaged with the emotion of having heard her sing anyway, it felt great. But this is the Francis Collins singing at the end of this concert.
I did my best, it wasn't much. I couldn't feel, so I tried to touch. I've told the truth, I didn't come to fool ya. And even though it all went wrong, I'll stand before the Lord in song with nothing on my lips but hallelujah.
So, biologically, we are what we do. And, what's next? We really want to understand what is going on in our brains. And I think that our fields have so much to unite and to interact and to bring together because we really want to be able to understand biologically what happens when people are engaged in music programs, and the music programs that you create. So I wanted to mention some of the folks in my lab who are responsible for pretty much everything that I have talked about today. And you can learn more about them on our website. And here is our magical website. And again, I encourage you to look at music, to look at neuroeducation, and to look at advocacy. So under advocacy, we've created a 2-page, it's a foldable flyer that you can give to parents, teachers, legislators, principals. It's the evidence. This is the biological evidence that I hope will be helpful to you, all in one place.
Thank you.
I'm going to leave you really with this brain keyboard, and I first want to explain to you what it is that we're doing here, and this is going to be fun. So you've seen that this is going on, right? So fact is, you've been listening to me. So you've learned a couple of things. Sound happens. Or doesn't. You have a microphone, which, when it's working, and yay team, transforms the sound waves, this movement of molecules, into electricity. And it is this electricity that then we feed into a speaker, right? So then you can listen to the sound that comes out of the speaker. This little guy can listen. We can put some sensors on his brain and measure electricity, which is the currency of the nervous system, right? So it's electricity, and we can play that back so that you can hear it. So I put to you, we have so much information biologically that we can begin to use and to think about. Imagine if we had a person, so, I have this musical keyboard where we have recorded the brain's response to every single note on the keyboard. So I can take, and you'll hear it sounds kind of noisy because the brain is always on. But the fact is, and if we have responses from different brains, and we can hear that each one of our brains has a different sound based on your life and sound. But imagine if you had the response of one of your clients before therapy and then after therapy. And how powerful for them, too, to be able to hear how their brain has changed in fundamental ways which are tremendously important for human communication. So let's do a little bit of brain playing. let's see. Hold on a second. Getting my brain to come up. Come on, guys, after this whole... Okay, maybe we've got it here. All right. Will you play just a couple of notes while I get the... Where are my glasses? I might have put them up here somewhere. Okay, now I can see. I think I was doing it right. I'm sorry, guys. Here we go. All right, go. Now, let me see if I can... Yeah. All right. So I think it would be great if we had some kind of jam going, right? So do we have a drummer, or do we have... And so I can get this better on the screen. A brain jam. Okay, so this is, yeah, nice. All right. Go. Ladies and gentlemen, is we have a lot to work with. And I think if we continue working together and we bring together the therapy and the science and the music all around, we're just going to get stronger and healthier. Thank you.